Okay, so let's consider the function f at x equals x squared minus 3 all over x minus 2. So we now have the methods to graph such a function. Last year we kind of graphed some pretty basic ones where we'd put in a vertical asymptote and a horizontal asymptote, picked some points, and we sketched it. But now we have a lot more happening in these graphs than what we had going on last year. So the first thing we want to consider is if the graph has any kind of symmetry. So the test is, how does f at x compare to f at negative x? And how does that compare to negative of f at x? So the function is x squared minus 3 over x minus 2. That is the function itself. And now if I replace x with negative x, I would have negative x squared minus 3 all over negative x minus 2. And I want to compare that to negative times the function f at x. So I have to distribute a negative either on top or the bottom, but not both, and compare them. So if I square this right here, I would get x squared minus 3 over negative x minus 2. That clearly does not equal the first function. If I distribute the negative on the top, I'd get negative x squared plus 3 over x minus 2. So that does not equal this function. Or if I had distributed the negative in the bottom, it still will not equal the function on the left. So therefore, f at x does not equal f at negative x. So this would mean that there is no y-axis symmetry, or it's not even. And since f at negative x does not equal negative f at x, the function is not odd and does not have origin symmetry. So this function, this graph, will have no symmetry. Okay, remember that if the first two are equal, it's an even function with symmetry with respect to the y-axis. And if these two here are equal, then it has origin symmetry, or it's an odd function. Number two, we want to consider the intercepts. Where will it pass through the x-axis and the y-axis? So the x-intercept, we will let y be 0 and solve for x. So that is, let 0 be equal to x squared minus 3 over x minus 2. A fraction equals 0 and the top is 0. X squared minus 3 equals 0. Add 3. And x equals plus or minus the square root of 3. So the x-intercepts are plus or minus the square root of 3, comma 0. The y-intercept is found as letting x be 0 and solve for y. So f at x, you know, is y. So y would be equal to 0 squared minus 3 over 0 minus 2. So y would be equal to negative 3 over negative 2, which equals 3 halves. So the y-intercept is 0, comma 3 halves. And these are the x-intercepts again. Next we want to look for any asymptotes. So step 3 is to find any asymptotes. Remember that vertical asymptotes, we have to first try and simplify the fraction if we can. And here we can't. So we will set the denominator equal to 0. That is, x minus 2 equals 0 when x equals 2. So there's a vertical there. Again, remember, vertical asymptotes only occur as if after you simplify the fraction, anything left in the denominator, when that equals 0, that's where there's a vertical asymptote at. The horizontal asymptotes, we know that we take the limit as x goes to positive and negative infinity of our function. So if I take the limit as x approaches infinity of f at x, it's the dominator theory. We're going towards infinity, so that the degree on top is 2, the degree on the bottom is 1. So the top wins, so that does not exist. It's just going up towards infinity. And that would also be true if we were going towards negative infinity. That limit would not exist. So there are no horizontal asymptotes. But what we do have here is not a horizontal asymptote, but we have an oblique asymptote. And this is occurring when the degree of the numerator, which is 2, is 1 more than the degree of the denominator, which is 1. This is x to the first, this is x to the second. So therefore we have no horizontal asymptote, but what we have is called a slant asymptote or an oblique. And how we figure that out is we'll just do some long division. So x minus 2 into x squared minus 3. So x times what gives us x squared? X. X times x is x squared minus 2x. Subtract, change the signs, add, can't combine those, so it's 2x minus 3. X times what would give us 2x? That's plus 2. 2 times x is 2x. 2 times negative 2 is negative 4. Subtract, and now we have our remainder. So this becomes x plus 2. So our slant is y equals x plus 2 plus the remainder of 1 over x minus 2. Now as x goes out towards infinity or negative infinity, this remainder will not matter and will approach 0. So therefore all we're concerned with graphing then is y equals x plus 2. So again, the slant asymptote occurs when the degree of the top is 1 more than the degree of the bottom. Do long division, or you could also do synthetic division. Okay, next we need to run a derivative test. Now we can run the information on f prime and f double prime. I'll need to erase that and then just recall the information back and trying to graph it. So recall that again, y or f at x equals the function x squared minus 3 over x minus 2. So y prime is a quotient rule, the bottom, times the derivative of the top, minus the top, times the derivative of the bottom, all over the bottom squared. So in cleaning up the top, we get y prime equals 2x times x is 2x squared, minus 2x times this is minus 4x, minus x squared plus 3 all over x minus 2 squared. Cleaning it up some more, 2x squared minus x squared is x squared, minus 4x plus 3 all over the bottom squared. And now in getting our critical numbers, we will set the derivative equal to 0. And the top would be equal to 0. Well, let's factor it. X minus 3 times x minus 1 all over x minus 2 squared. So we can easily see that the top is equal to 0 when x equals 3 and x equals 1. The bottom, the derivative is a d and e when x equals 2. But if you go back to the original function, which is up here, 2 is not in the domain of f. So therefore that's not a valid critical number. Okay, so let's run a number line test for f or f prime or y prime at 1 and 3. So if we pick 0, we can put it here. That's a negative times a negative, which is a positive. And we'll also, I do note that my bottom is automatically positive because anything squared here is positive. I do have a vertical asymptote here at 2, so I can't obviously include 2. If I pick, say, 1.5, I will get a negative times a positive over a positive is a negative. And if I pick, say, 5, I'll get a positive times a positive over a positive is clearly a positive. So the function here is increasing, decreasing, and increasing. And what's important to realize is the extrema we have. That we have a relative max at x equals 1 because f prime changes sign from positive to negative. And we have a relative minimum at x equals 3 because f prime changes sign from negative to positive there. And we get the y values by substituting them all back. Okay, so now let's make a sketch of it using all the information that we have. That is the goal of this problem, is to sketch this function which we could not do last year because of the fact we did not know any relative extrema. We couldn't find it. We didn't use the derivative test at that point to find the relative extrema. So now we're able to graph such rational functions using the first and perhaps the second derivative test. So now let's pull it together for a graph. So using all the information in the previous parts, the last step is to sketch a graph of it. That is the essential goal, is to come up with the information to make an accurate sketch of f. So here is x, and here is y, and we'll count out here 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so let's put in our vertical asymptote, which is at x equals 2. So just to recall that there was a vertical at x equals 2. There it is. Let's put in the slant. There was a slant, as you recall, at y equals x plus 2. So that's up 2. Up 1 to the right 1. Up 1 to the right 1. And up 1 to the right 1. And there's the slant asymptote. And then we did have some intercepts. We had the x-intercept at plus or minus the square root of 3, 0. So that's about plus or minus 1.7. So just over 1.5 in this direction. And then just over here, negative 1.5 in that direction. And we also had a y-intercept at 0, 3 halves. So that is 0 up 1.5. And now we've got the turning points. We had a relative max at x equals 1. You have to substitute that back into the function to get the y value. And that came out to be 2. And we had a relative min at the point 3, 6. So again, at x equals 3 is a relative min. Substituting it back into the function, we get y is 6. So then over 1 up 2 is the relative max, and over 3 up 6. 1, 2, 3, 4, 5, 6 is right here. And now we'll use the asymptotes as a guide. So here we'll connect through, reaching up to the relative max, turning around, and approaching the asymptotes. And then again here, using the asymptotes as giving shape to the graph. And there's that piece, as we call these sometimes the branches of the graph. Remember, what's interesting about this graph as well is as x approaches positive infinity, we pretty much know what the y's are tending towards. As x goes out to positive infinity, the y's are approaching the y's on this line. So if we remember that that line is given as y equals x plus 2. So out at 1,000,000, the y value is about 1,000,002. And we can also take it towards negative infinity. As we approach negative infinity, the y values are approaching this line. You want to know what approximately is that y value as you go out towards negative infinity. Substitute the value in for x and add 2. What's interesting to note is that right here, this is the relative maximum, and this right here is the relative minimum. If you look at the graph as a whole, you realize that the relative maximum is actually lower than the relative minimum. So here on this graph, and standing back and looking at it, you see that locally speaking, this is the high point. But it is not the highest point, obviously, on the graph. But locally speaking, that is a high point. And locally speaking here, that is a low point. And what's interesting, again, to note is that the relative min is actually higher than the relative maximum. Remember also from the first derivative test, just so that it all stacks up and makes sense to us, is that from the first derivative we learned that these were the critical points, 1 and 3, and f prime was positive, negative, and positive. So here, from negative infinity up until 1, f is increasing. This is f increasing from negative infinity up until 1. It then decreases from 1 to 3. So this is a 1. There's a vertical at 2. Now as we pick up and resume the graph, still this graph is falling. It is still decreasing until it hits x is equal to 3. And then it increases away from it. That as x gets big, the y's are getting big, and therefore we have a relative min there. So it does match up, that this is increasing here, decreasing, and increasing. So once again, as we approach 1 from the left, f is increasing. It then turns around and is decreasing. But now as we resume the graph, on the right side of the vertical asymptote, we see that it is falling from left to right until it hits x is 3, and then forever increasing.